Hello and welcome to today's webinar from Element 14 in collaboration with Texas Instruments. Today's presentation will be from start to finish, creating a multi-node cloud-connected sensor network featuring a selection of Texas Instruments Launchpad development kits. If you have any questions for Adrian throughout the webinar, please use the Q&A function found in the drop-down menu of the green taskbar of the WebEx application. If you have any technical issues during the presentation, you can chat me at Premier Farnell Webinars directly by using the chat function found also on the green taskbar of the WebEx application. A recording of this presentation will be made available on the event page you registered from on the Element 14 community later today. Additionally, I'd like to announce that we're now taking applications to road test this multi-node bundle that Adrian will be discussing. If you find this link, you can find the link and more information on the event page for this webinar or visit our road test page at element14.com/roadtest. So without further ado, I'm going to turn it over to our presenter, Adrian, who's going to walk through the presentation. Thanks so much.
Great. Thank you, Dave, for the wonderful introduction. I'm glad to be here. And as Dave mentioned, we'll be creating a cloud-connected multi-node sensor network here today from start to finish. We're going to be leveraging the Texas Instruments Launchpad development ecosystem, which is our portfolio of modular open-source hardware building blocks that engineers, developers, and makers can plug together to create complete systems and complete products. In this case, I have a multi-sensor node network that will communicate over a sub-gigahertz RF radio. Each of these nodes will read different types of sensor data. We'll actually be building 3 nodes here today, a sensor node that will detect moisture or the presence of water. We'll have another sensor node detecting the ambient light reading of my office. And then a third sensor, which will be a simple potentiometer turn knob. So each of these nodes will read a sensor value, print it out to an LCD screen, and also send out those readings over the RF radio to a cloud-connected Wi-Fi-enabled gateway. And that Wi-Fi-enabled gateway will be able to collect and aggregate the data coming from the multiple sub-gigahertz sensor nodes and then publish that up to the cloud over Wi-Fi using a IoT protocol called MQTT. So without further ado, let's go ahead and jump into the slides. And as Dave mentioned, please use the chat functionality if you have any questions, and we'll do our best to address those at the end of the webinar. In addition to that, we are, in addition to the road test, there is a chance to also win some of the hardware that we're demonstrating here today. And you'll learn more about how you can get your chance to get a hold of that hardware for free if you stick around to the end of this presentation. So let's go ahead and jump right in. So what are we doing here today? So we've got about an hour together. I'm super excited to spend the day with you. First, I'll give a brief introduction to the Launchpad portfolio. If you're not already familiar with it, we'll talk about some of the hardware, software, and resources available inside of that ecosystem. We'll spend a bulk of our time, most of the time here today, doing a live build. So as I mentioned, we're basically going to break down our system into 3 parts. We'll have the individual sub-gigahertz RF sensor nodes. That'll be part number 1. Part number 2 is going to be the Wi-Fi sub-gigahertz RF bridge, the gateway that will aggregate the sensor data and communicate to the cloud. And then lastly, the cloud side of the system. You know, once we have our data being sent up to our web service, what can we do with that data? With the promise of IoT, we have the ability of doing data visualization. We can enable remote notification. So if I'm not at home or I'm not in the office, I should be able to open up an app or navigate to a website and visualize some of my sensor data that way. And then there's also the promise of big data analytics. Once we have data being accumulated into a database, we should be able to perform algorithms on that data or find line of best fit to identify trends. So we'll touch on some of those here today. And then, as I mentioned, if you stay tuned, you'll have a chance to actually receive some of this hardware that we're going through here today. So definitely stay tuned for that. So a quick introduction. My name's Adrian. I'm the product manager of the TI Launchpad ecosystem at Texas Instruments. I would identify myself as a maker. I'm also a TI engineer, obviously, working at the company for about 6 years now. But I would also consider myself a IoT or Internet of Things and open source evangelist. I'm a strong believer in enabling more engineers, students, and makers with open source hardware. This helps developers get up and running much more quickly, and you don't have to reinvent the wheel every single time. And hopefully, as we rapidly prototype our our hardware here today, you'll be able to see how we're able to reuse a lot of existing building blocks. If I need a RF module, I don't have to create a new schematic or a new board layout. I can simply use an existing plug-in module or booster pack and plug that on top of my microcontroller development board. So hopefully you'll get a taste of some of that here. I also graduated from UT Austin here in Texas, and I've been at TI ever since. So it's been a pleasure, and it's always great to do these webinars to showcase some of the cool new technology that TI is releasing for enabling the up-and-coming engineers. And then feel free to follow me on Twitter. I try to post there as often as I can, typically around the concept of development tools, IoT, and other industry trends. So definitely take a look and feel free to follow me if you so choose. So in short, the main goal of the Launchpad portfolio is to enable rapid prototyping, and we were able to do so with open source hardware and open source software tools. We've done several webinars through Element 14 in the past, and hopefully you've had an opportunity to participate in some of those, and I'm sure they're probably available on demand as well. So if you are curious, definitely take a look and see some of the previous webinars that we've done where we do talk about some of the other tools that are available within this ecosystem. But in short, the goal is to enable rapid prototyping. And when you think about rapid prototyping, almost anyone can benefit from that sort of development philosophy, whether you're a student, whether you're a maker or a hobbyist, whether you're a professional engineer in a Fortune 100 company. Rapid prototyping is, I think, a critical component to product design and the overall product lifecycle as you go through your development flows. It allows you to get to something up and running much more quickly so that you can start accumulating customer feedback. And it allows you to go through several iteration loops until you finally have the final product that meets a customer demand. And I think the tools that we'll be showcasing here today will demonstrate how that's possible. Here's a bird's eye view of the Launchpad ecosystem. We have about almost 18, I think, different Launchpad kits. We've got quite a few different variants, and you can see a snapshot of them here at the bottom. From the ultra-low power MSP430 device, which is what we'll be using here today for our sub-gigahertz RF sensor nodes, all the way up to our new Hercules ARM Cortex-R microcontrollers. We even have some Launchpad kits with integrated Wi-Fi with a CC3200 kit. And this kit is actually going to be the heart of our Wi-Fi gateway. So this Launchpad here will basically aggregate the data coming from our multiple MSP-powered sensor nodes. In addition to that, we have an ecosystem of plug-in modules, and we call these booster packs. We've got about 80 different booster packs today coming from TI as well as third-party partners. And this allows you to, again, enable complete systems by leveraging pre-existing open-source hardware. So if you need a temperature sensor or you need an e-paper display or a battery pack with a BQ fuel gauge, you can pick and choose these components as needed to build that system. In addition, TI has a wide selection of wireless RF network processors. Whether you need sub-gigahertz RF to 2.4 gigahertz technologies such as Bluetooth, Bluetooth Low Energy, or Wi-Fi, we have the complete sort of RF spectrum represented in the booster pack form factor. So in this case, we're going to be using the CC11OL booster pack here, which will serve as our sub-gigahertz RF network processor. And that's how our various sensor nodes will send data to our Wi-Fi gateway. And as this image here implies, you can actually stack multiple booster packs along the Z-axis. So that means you can actually have 1, 2, 3 booster packs plugged into a single Launchpad to enable a more complex, feature-rich application. And here are just a few demo recipes. I won't go into every single one, but this just gives you a taste of what's possible as you start mixing and matching these various modules. One example here, this is one of our favorite ones to demonstrate at trade shows or at conferences, is a internet-connected barbecue sensor. So we are from Texas, right, being Texas Instruments, and we like our barbecue here. So we actually have internet-connected meat thermometers. So you can actually buy this booster pack from the TI e-store, as well as from Element 14 and other distribution channels. It comes with this K-type thermocouple you can actually plug into your hamburger or your steak or your Wiener Schnitzel, right? Whatever it is you're making. And with the Wi-Fi booster pack, we can actually send temperature data up to the cloud and enable remote notification or maybe an SMS text message when your meat is finally ready. And that's all possible by just simply plugging these boards together. So all of our launch pads, we have, again, about 18 different variants today ranging in functionality and features. They all have a standardized pin-out connection. So this enables each of the launch pads to tap into the booster pack portfolio. So we know that the power and ground pins will always be in the same spot. The analog capable pins are always in the same space, as well as the SPI, I2C, and UART pins. So for the most part, all of the common interfaces you come to expect from a microcontroller are going to be brought out consistently through the booster pack connector. And all of the pins on our launchpad boards are on a 100 mil pitch. So that makes it really easy to leverage a perf board or a prototyping board to again, rapidly create your system. And I know we're talking a little bit more on the scope of IoT today, so I wanted to talk a little bit about our cloud partners that we work with. This is just a small sampling of some of the cloud services that offer support for our Launchpad development tools. We work with IBM. We work with companies like Exosite and ThinkSpeak. We also work with companies like PubNub. And each of these cloud service providers provides something a little bit different. Yeah, they all might do some data aggregation and data visualization, but they all provide different business models, different plans that are available for you. So I encourage you to take a look at ti.com/IoT, which is a portal that we put together that talks a lot about the various partners that we have here today. For our particular demo here, I'll actually be using an IBM cloud for the demonstration that we're looking at specifically. And maybe the last slide before I jump over to the hands-on component, because I really want to spend most of my time there, is an overview of our software tool chain. For Launchpad, we have multiple points of entry, different development environments available depending on the type of developer you might be. If you are more on the maker side or if you're familiar with programming on an Arduino, we have the Energia framework. Energia is a fork of the open source wiring and Arduino API framework. We've even forked the open source IDE, so we're now code compatible with those devices. So a lot of the code examples, libraries, and example projects will now compile on many of our Launchpad development kits. So that's one option. You can use the Energia IDE, and we'll actually be using that here today for parts of our application that we're building. Secondly, this one's most recent. We just announced a new Cloud IDE. I'll also be using this tool so I can demonstrate some of the features that that platform provides. But it basically provides you with a complete code editor and code compiler tool, all developed inside of a web browser. So you can open up a new tab in Chrome or Firefox and actually do your code editing inside of the web browser. And this allows you to get up and running more quickly and not have to worry about a lengthy install process before you can start being productive with code development. Then lastly, we have our more traditional development environments. We have TI's Code Composer Studio, which is our Eclipse-based IDE, but then we also support IAR and Kyle. So depending on the Launchpad you're using, we might have additional development environment options as well. So as you can see here, a full range of development tools available for you. And you have multiple layers of abstraction that you can use when doing your firmware development. You can use the Energia or wiring APIs, which abstract away the sort of register level programming. And this provides you with an easy way of programming your microcontroller without having to worry about the bits and bytes traditionally required when programming a microcontroller peripheral. In addition to that, you can also use traditional C code or even assembly if you so choose. So lots of different programming options available for the developer. The good news is that Energia and CCS Cloud are cross-platform, Windows, Mac, and Linux. CCS today is supported by Windows and Linux, and we actually have a beta now for Mac support. So for the most part, these three primary development environments that I'm showcasing here are cross-platform from Windows, Mac, and Linux. And I think that's pretty differentiated when you look at some of the other silicon vendors out there. So without further ado, let's go ahead and jump to the workshop. I actually documented a lot of what I will be doing here today on this URL called hackster.io. They're a great company that we've been working with for enabling project repositories. So you can actually navigate to the Hackster page and see, I think, about 100 different Launchpad projects that have been contributed by both TI as well as the online community. So I'm going to go ahead and switch gears here and show you that website. So I'm going to bring in my browser so you can actually see what we're talking about here. There you go. And this link here is available in the slides. I'll also put it into the chat here. Let's see if I can figure out how to do that so you guys can scroll through it while I'm giving my presentation and demo. But navigate to that URL, and I did my best to completely go over and document the various components of this system. So by following this tutorial, you should be able to recreate everything that we're doing here. So you can go ahead and take a look at that. Okay. Whoops, actually, I sent the wrong link. Let me send you this one instead. Apologize for the mismatch here. There you go. So that link there will take you to this exact same page, and this is actually where I'm going to be pulling some code from as we build our sensor network. So I've got some embedded videos here to kind of showcase what exactly we're building, and for the most part, you all should be able to follow along. So if you want to replicate this setup on your own time, feel free to navigate back to this URL and recreate some of these steps. And as Dave mentioned from the Element 14 team, we're doing the road test as well. So for those participating in the road test, you can go ahead and follow these tutorials to get up and running with that hardware. Great. So before I go and start building stuff, I actually want to give you a demo of it all working together. So let me switch over to my camera here. Let's see if I can pull this up. There you go. Y'all should basically see my cell phone screen. So I'm going to switch to the camera view so you can actually see the hardware that I have here in front of me. So this is a sensor node that we're going to be building today. This is featuring the MSP430 FR69 microcontroller launchpad. This is available for about $15, so pretty affordable. It's hooked up to a potentiometer knob, as you can see here, and I'm printing out the real-time sensor readings to the LCD screen. You can also see a red LED blinking as well as a little TX symbol blinking on the segmented LCD display. So those are going to toggle off and on every time I'm sending a new RF packet using the RF booster pack. So I simply plugged these two boards together and I hooked up my potentiometer sensor to one of the analog capable pins of my launchpad. And again, this is all documented on the URL that I just sent you. But for the most part, you can see that the hardware is very simple. I just took a pre-existing Launchpad microcontroller board. I plugged in our RF radio booster pack, and I hooked up an analog sensor. And using some code, I programmed it to read the sensor data, encode it into a JSON payload, print out the latest sensor reading to the LCD screen, and then using the segmented LCD and the red LED, I'm able to notify visually to the user when we're sending new RF data. So when I turn the potentiometer knob here, you'll see that the value changes appropriately on the segmented LCD display. And you'll see that this is actually a really high resolution A to D. So I'm going to go all the way up to 4095 on this MSP430 device. In addition to that, we have two other sensor nodes. This one here is an ambient light sensor. So it's identical to this other node. The only difference is that I have an ambient light sensor hooked up instead. And these sensors are coming from a company called Seed Studio. We work with them very closely, and they have a starter kit for the Launchpad that includes many of these sensors. But you can see that my office is well lit, and you can see some of the readings there. But if I cover up the sensor, you see that those values go down appropriately. If I let go, you'll see those readings spike back up again, so on and so forth. And just like before, the red LED and the little TX symbol is blinking to notify us that we are indeed sending our sensor data. And then lastly, the last sensor I have here is a moisture sensor. You can stick this into your flower pot, so you can actually now monitor your plants, make sure they're getting enough water. Right now, there's no reading, but if I were to take my cup here, and there's some condensation, some water on the side, you'll see that that value should shoot up here. There you go. So you can see that it's seeing that increase in moisture. And just like before, we're sending those data points. So this here is our Wi-Fi gateway. So this is, again, another simple creation, simply using our CC3200 Wi-Fi launchpad paired with the same RF radio booster pack. So this radio here enables it to receive the data points coming from the individual nodes. The CC3200 launchpad actually has built-in Wi-Fi. So this is right here, the Wi-Fi antenna circuitry. You can also see some of that. And there's a CC3200 microcontroller right there in the middle. And that is a ARM MCU with an integrated Wi-Fi processor. So in a single chip, you get a application MCU plus Wi-Fi connectivity. And by pairing these two boards together, we're able to communicate over the sub-gigahertz RF as well as Wi-Fi. And I have a Wi-Fi hotspot set up here. And you can see that the green LED means I'm connected to Wi-Fi. The red LED means it's receiving data points from the nodes. And the yellow LED signifies that we're publishing those data points up to the cloud. So I'm going to go ahead and minimize this here. Or actually, I'll leave it open. And here you can see is our dashboard. So you can see some of our sensor data now streaming through. So let me see if I can zoom out here so you can see more of our dashboard. There you go. Then I'm going to bring up the video so you can actually see what's going on here. So if I turn the potentiometer knob, pay attention to the graph there. You can see as I turn the knob all the way to the left, this values go up. Turn it all the way to the right, it goes back down. And there's very little latency here. MQTT, which is the protocol that we're using to forward our data points up to the cloud, is a very lightweight, very fast publishing protocol. So my launchpad here, my Wi-Fi gateway, is the publisher, and my cloud service is the subscriber. So it's basically a nice sort of bidirectional communication protocol for IoT devices in the cloud. In addition to that, if I cover up the ambient light sensor, you see that the data points are reflected appropriately in the web dashboard. And one thing I'll go ahead and do is I'll actually send you this link. Because this is in the cloud, this is a public dashboard that everyone can get access to. So you guys will be able to visualize my sensor data in real time by navigating to that URL. So I'll let you guys click there, and you'll be able to see all of the data streaming through. So if I cover up my ambient light sensor, again, the value will go down, so on and so forth. Let me close this out here. I think I'm done with my real-world hardware. So again, I'll just play with some of these sensors so that as you guys are connecting to the dashboard, you'll be able to see the data points change appropriately. So you should see some spikes in the water values. You should be able to see my potentiometer values, etc. So it's all working appropriately. Great. So now that you've seen the demo, I'd like to now spend some time building the product. So first and foremost, I've got my MSP430 launchpad plugged in over USB. And now that we've seen the hardware setup, let's go ahead and program it to serve as our wireless sensor node. So I'm plugging my launchpad in over USB now. And I'm going to be using CCS Cloud to program my launchpad. So you can navigate to dev.ti.com, and this is where you can get access to our new cloud IDE called CCS Cloud. I'm just going to click on that, and I'm going to log in. So if you guys actually create your own account, you'll be able to do everything that I'm doing here today in terms of doing code development in a web browser. So give it a second here to log in. You can see it's preparing my workspace, and now this is a cloud-hosted workspace. So I can actually log off. I can go to a different computer, or I can go home. I can log back in and actually continue my web development or code development because all of my code is hosted in the cloud underneath my TI login page. Excuse me. There we go. So you can see now it's all up here ready to go. And I've already created a project here that has the code for my wireless sensor node. And to create your own project, you simply go here to Project, New Energia sketch, since that's the type of programming language we're using here today. And you choose which platform you're using. In this case, we're using the MSP430 FR6989. So we want to make sure that we tell the IDE which microcontroller and launchpad we're using. Then we can go ahead and give it a name. So I can say this is my sub-gigahertz RF sensor node. And I can go ahead and click on Empty Sketch so I can leverage one of these templates and hit Finish. And that will basically create a brand new project here in my workspace. But I've already done so. So let's go ahead and switch gears here. And I can see that I've got various code files inside of my new project that we've just created. There's a main.ino file. This is the main application that we're going to compile and flash to our hardware. We also have a CPP and .h file. These are library files that we're using to update the values on the LCD screen. The good news is that all that code is available here in the Hackster link that I sent you. So when you navigate back to this page, you can actually scroll all the way down to the bottom where we have a code section. And you'll be able to copy and paste this code into CCS Cloud. So this first project here is the main firmware for our sensor node. So you can actually select all this code here and copy and paste it into your main.ino file. And that's the code that we've got here. In addition, I also have the library files. So here's the lcd.cpp, the C++ file, the lcd.h file, and the keywords.txt file. So these three files make up the LCD Launchpad library. And I simply, again, just copy and paste the contents into the appropriate files here. So you can see I've got an LCD C++ file, I've got a .h file, and I have a keywords file. And all of that code was copied and pasted from the tutorial page. So now that we have all the code files available, let's go ahead and scroll through the code line by line to give you an idea of what's happening at my sensor node. So at the very top, we do have some comment blocks. The first real line of code we have is a few lines for importing the required libraries for our sensor node. We need a SPI library. That's the actual interface between our RF radio and the microcontroller. This is the CC11OL RF radio. So this library here exposes very easy-to-use APIs for leveraging the radio. So we have APIs like radio.transmit, for example. And with that one line of code, I'll be able to send payloads or RF packets to anyone who's listening. And another library I'm using is called AJSON. For those who are familiar with JSON, it's a lightweight sort of data formatting tool that we can use. So it's a way of organizing and encoding our data so that it's very easy to parse and decipher. And I'll show you what that sensor data looks like later. And then lastly, here's the LCD library that we just manually imported with these files that we brought in from Hackster. Cool. We also have a few global variables. This is the analog pin that our sensor is hooked up to. I also gave my sensor a name. I named him Henry. You can name him whatever you want. And then the type of sensor value. So in this case, this is my potentiometer node that I have plugged in over my computer. So by just simply changing these three lines of code, we can basically tell the sensor node what type of sensor it is. And we're going to encode this information into the JSON payload so that when I send it out to our Wi-Fi gateway and ultimately to the cloud application will know where this data is coming from. He'll understand that this is coming from sensor named Henry and he's a potentiometer. And that'll be important as we start doing our data visualization and other types of data management in the cloud side. Scrolling down is a function that I created for scrolling text on the LCD display. So the main line of code here is my LCD.displayText, and we can simply pass it a string. And that one line of code will basically print the required characters onto the LCD display. But I'm also wanting to scroll it so that I get kind of a scrolling marquee effect. And I'm able to do that by simply finding the substring of that string and reprinting it back to the LCD until there are no more characters on the string. And then we can scroll down, and this is really where the main application lives. If you're familiar with Arduino or Energia or wiring, your application is broken up into two sections. There's a setup and a loop section. In the setup section, this runs once at the beginning of code execution, and we do just a few things. First, we set up our UART, our serial port, And with one line of code, it's configured at 9600 bits per second, and this enables my Launchpad to send data back and forth over the USB port. The second line of code is radio.begin. Again, this is the one API that's provided by the radio library that we imported earlier. And with this one line of code, my radio is ready to use. It's configured at a particular RF channel. This is a 915 megahertz radio. We configured it for max power to amplify the range that we're able to get with this node. And I'm going to go ahead and give it an ID of 0x01. So one line of code, my radio is ready to use. Secondly, my LCD.init. This configures the onboard LCD of the Launchpad. And again, with one line of code, the LCD is ready to use. The rest is actually not too complex. The next thing we do is we print to the LCD the type of sensor it is. So my sensor, if you remember, is the global variable up here that says potentiometer. So at the beginning of code execution, we'll actually print out potentiometer sensor to the LCD screen, so that when you plug it into USB power, you'll be able to identify the type of sensor this is by simply reading the LCD. And then that's pretty much it. The next thing we do is we configure our red LED as an output pin so that we can use it in our main loop, which is going to basically blip that red LED every time we send a new RF packet. Scrolling down to the loop section, anything we place between the loop brackets will just loop forever and ever. So this is kind of our main.c, if you will. First thing we do is we turn the red LED high, turning it on to signify that we're starting a new RF packet. I also have that little TX symbol that's on my segmented LCD display. With this one line of code, I'm able to basically enable that segment of the LCD, and that's how we got that little tiny TX icon to appear on the LCD screen. This is the desired JSON format. So if you're familiar with JSON, this shouldn't look too unfamiliar. This is what JSON encoded messages look like. And as you can see, it's just a really nice way of organizing data. So for each RF packet, we'll have a name object, we'll have a sensor object, and a data object. And anyone who receives this packet will be able to decode the JSON and easily find the information that it cares about. The AJSON library that we imported provides a few easy-to-use APIs for encoding JSON. So this allows me to add a string to my JSON object. In this case, I'm going to add the name and the sensor type. I can also add a number to the JSON object. And in this case, this is going to be the sensor reading that's being provided by my analog read API. So with analog read, I'll be able to read the incoming sensor data coming from my sensor. The next important line of code is radio.transmit. This is going to basically send out the JSON payload that we just encoded up here, and this will send it out to anyone who's listening. So with that one line of code, we just now sent out our JSON encoded messages. Then we print out our sensor value to the display. And then ultimately, we go ahead and turn off that red LED and turn off that segmented LCD. And then we delay for 250 milliseconds. So this delay here will determine how often we're sending new sensor data. And in this case, it'll be 4 times a second, since we're delaying by 250 milliseconds per RF transmission. So let's go ahead and compile this code. I'll hit this hammer button here. There you go. You can see build finished. And I can go ahead and hit the flash button. And this is going to program my MSP430 Launchpad that's plugged in over USB. There you go. You can see loading complete. CCS COD has a built-in terminal, so I'm going to click on Connect COM port. I'm going to click on the appropriate COM port, and I'm using 9600 bits per second as we defined in the firmware. So I'll hit OK. And now you can see my JSON encoded messages printing to the terminal because we actually print them out using the serial print function. So in addition to sending it over RF, I'm also printing it over the USB port. So when I turn the knob here, you'll see that the values are changing and my JSON messages are updating appropriately. So that's it for my sensor node. So the only thing I need to change to enable my other sensors is these lines of code here. So if I wanted to give my moisture sensor the name Adrian, I simply change those 2 lines of code and I can compile it and flash it to my other nodes. Because again, they're electrically identical. The moisture sensor and the light sensor are hooked up to pin 23 as well, so I don't have to change this line of code. The only difference is I'm basically changing some of the items inside of the JSON payload so that it can identify itself appropriately when I get that data in the cloud. So hopefully that all made sense. That was basically us creating our RF sensor node. We would repeat this step 3 times for the 3 different nodes that we have here, and we'll be in good shape. The next thing I'll go ahead and do is show you the code for the Wi-Fi gateway. So the gateway, if we remember, is based on the CC3200 launchpad. So I'll show you a picture of that. That's this guy. We saw it earlier on the video. But it's basically the CC3200 launchpad paired with the RF booster pack. You plug those 2 things together, and you've got yourself a RF to Wi-Fi bridge. So I'm going to go ahead and plug that into my USB port this time so that we can do some of the code development for that side of the system. So I'm plugging it in over USB now. And to program this guy, I'm actually not going to use CCS Cloud. I'm going to use Energia just to showcase to you what that development environment looks like. So if you haven't programmed with Energia before, it's a very simple IDE. As you can see here, it's very simple looking. It's very lightweight. There's not a lot of features, but it's enough for you to do code development and code compilation. So this code here I've actually pulled again from the tutorial page. So if you go back to our tutorial page and scroll down, you'll actually find the gateway code here. So sub-gigahertz Wi-Fi gateway firmware. And then again, you can copy and paste this code into the development environment you choose to develop with, whether that's the cloud environment or the offline IDE. So I've already copied and pasted this code in. And let me scroll through it again just like before to give you an idea of what's going on here. Again, several libraries that we're using. We do need a Wi-Fi library and the MQTT library. So again, MQTT is the communication protocol that we're using. We do have some global variables here, such as the Wi-Fi credentials. So that's my SSID and password for my Wi-Fi hotspot here. And this is the MQTT broker that we're using. So for MQTT, there's 3 players for every communication message. There's a publisher, in this case my Wi-Fi gateway. There's a broker who's sort of a middleman who brokers all of the different messages, and then there's a subscriber. And what's nice about MQTT is that it's almost like Twitter for hardware. Depending on how many subscribers or followers you have is how many folks or things or services will receive your data. So if my Wi-Fi gateway here publishes data and it only has 1 subscriber, like a cloud service, that cloud service will receive that data. But I might have maybe 10 cloud services subscribed to that data point, or maybe 100 launchpads, etc. So it could be a one-to-one communication or one-to-many. And that's the nice thing about MQTT. Scrolling down to the main application, again, we have our setup section. I'm going to set up a couple of LEDs, a red LED, green LED, and yellow LED, and those will basically provide visual notifications on different states of the system. I configure the serial port again so that I can receive my data points. And then I'm going to connect to Wi-Fi. So really with just 1 line of code, Wi-Fi.begin, I just pass in my SSID and password, and my Wi-Fi launchpad will connect to Wi-Fi. And then the last thing I do in setup is radio.begin. So just like before, I'm going to configure my radio, and it'll now be able to receive incoming RF messages. So that's it in setup. All we really did was configure our UART, connect to Wi-Fi, and initialize the radio. And now in the loop section, this is our main, again, application section. I'm going to connect to my MQTT broker, so client.connect. And this is going to enable me now to start publishing data to that broker. And once I'm connected to the broker, I'm going to turn on my RF radio. And I'm going to basically just sniff the air to see if there's any incoming messages available for me to receive and process. And if so, I call a function called printRxData. So if I scroll up to the top to that function, we'll see what happens in there. So this function here will only be called when an RF packet is received by the rf.receiverOn function we saw earlier in the main loop. And anytime I receive data, I'm going to print out some diagnostic information to the terminal. And I'm going to publish the RX data that we just received over RF. So every time it receives a new payload coming from one of the sensor nodes, it's going to publish it up to the cloud using MQTT, using the library that we imported. And with this one line of code, client.publish, I'm able to publish and forward up the RF sensor node that's encoded in JSON to the cloud. So with MQTT, again, there's really two things you need to enable. One, you need to connect to the MQTT broker, which we did using the client.connect function. Then you need to publish your data to a certain topic. So there are multiple things connected to a broker. And in order to pair publishers and subscribers, there's a topic that can be used. And that topic is what a publisher will publish to, and it's the topic that a subscriber will subscribe to. So in this case, we're going to publish our data to this topic, mySensorData_Adrian. So this Launchpad has already been programmed. I can do so by clicking on this arrow button. This will compile the code that we've just written, flash it to our hardware. Energia also features a built-in serial port, and you can access it by clicking on this magnifying glass. And you can see that it's receiving data points from my sensor data. So you can see water, light, and potentiometer. It's moving pretty fast because each of our sensor nodes are sending 4 times a second. But the good news here is that we are able to confirm that our Wi-Fi gateway is receiving those RX payloads and printing it here to the terminal. You can also see here that it says MQTT publish success. And we print that here in our RF packet received function. So if we are able to publish our sensor data to this MQTT payload, not only do I toggle a yellow LED on and off, but I also print to the terminal MQTT publish success. So just like that, we programmed both our sensor nodes and our Wi-Fi gateways. So hopefully that's all made sense so far. The next thing that I'll go ahead and switch my attention to is the cloud. So when you think about IoT, there's really 2 worlds we need to develop in. The real world, right, which is our hardware, it's our sensors, it's our launch pads. And then we have our cloud, which is going to receive some of the data that our Launchpad is publishing up over MQTT. So now that we've confirmed by looking at the serial port that our Wi-Fi gateway is indeed receiving data from our sensor nodes, and you can see that it's conserving the appropriate JSON encoded messages, we can turn our attention to the cloud. So I'm going to navigate to a web browser here, and I'm going to navigate to a tool called Node-RED. So this tool here is what we're using to build our cloud-side application. Node-RED is a JavaScript Node.js-based graphical tool for building cloud-side applications. So you can actually run Node-RED on any Node.js runtime. So if you want to run Node.js on your Linux computer, your Windows computer, your BeagleBone Black, you can actually run Node.js and Node-RED on those platforms. However, companies like IBM, we've worked with them to enable Node.js to actually run on their cloud service. So instead of you having to have a physical Linux box or Windows box to run Node.js, with a single click of a button, you can actually tell the IBM Cloud to host one on your behalf. And that's actually what we've done here. So the IBM Cloud service is called Bluemix. And this application is running on the cloud and hosting its own Node.js runtime and hosting the Node-RED application on top of that. So you can actually create your own Bluemix-hosted Node.js server by navigating to bluemix.net and creating an account. And they have several examples and boilerplates on how you can create your own Node-RED instance running on their cloud. And that'll take maybe about 5 minutes between the time you click instantiate my cloud service and the time you can start playing with your cloud. So it's actually really fast for them to spin up those servers on your behalf. So once you've created your own Node-RED instance, whether it's on your BeagleBone or on your Linux box or in the cloud, you'll have your own Node-RED palette, which will look like this. And it's very blank at the moment. So let me make a few modifications here real quick. So yours will be blank. As you can see, I have a few applications, a few projects here already. But just to give you a brief overview of how this works, Node-RED is a graphical tool, and they call these flows, where these nodes here that you can pull from this palette interact with each other. So I can hit deploy, and this application will basically print out a timestamp and send it out over MQTT. But I actually don't care about MQTT right now. I want to print it out just to this debug window. So if I click these two things together, hit deploy, And when I hit this timestamp button, you see the timestamp being printed to the debug window. And that's just how Node-RED works. Basically, it's nodes communicating to each other. So if I click the timestamp, flows out, prints to the terminal here. And you're seeing a lot of sort of artifact debug messages coming from some of my other projects. So that's cool. I can also double-click on this node and say, instead of a timestamp, I want a string that says hello world. I can go ahead and hit OK, redeploy. And now when I click on this button, I get hello world there in the debug window instead. Great. So what if I wanted to replace that wire with an MQTT interface instead? So I could actually drag in this MQTT block, hit and configure my MQTT. So this is the same IoT broker that we're using. I need to publish to a unique topic, and I want to subscribe to a unique topic. So what we've just created are two cloud-hosted MQTT publishers and an MQTT subscriber. So anytime I click the Hello World button, it should publish that string over MQTT to this unique topic that this subscriber is listening to. So he should be able to receive that data. It'll flow out and then hit the debug window. So let me clean this out. And just like before, we should see Hello World. There we go. So you can see that it's working perfectly. Now we're using MQTT instead as the interface between these blocks. Cool. So now let's go ahead and create a subscriber that will receive the data that our Wi-Fi Launchpad is publishing to. So if I switch back here, you can see I'm using the same MQTT block. I just configured it to listen to the topic that my Wi-Fi Launchpad is publishing to. So if we go back to our Launchpad code here, we can see that with this one line of code, client.publish, my Launchpad is publishing the RF data it's receiving to mySensorData_Adrian. So that's the exact same topic that I'm subscribing to here in the cloud. So when I hit OK, and I hook up my message payload, my debug block, to that node, and hit deploy, and open up my debug window, you'll see that my data points are coming in through the cloud. So this is the same exact data that we were receiving earlier. So this MQTT receive block is receiving the data that my hardware sitting here in my office is tossing up into the cloud. And I'm now printing it to the debug window, as you can see here. So just like that, we've bridged the two worlds. We've bridged the hardware world with the cloud world. And now that my real-world data is in the cloud, anyone who's web-savvy can start doing very powerful things with this data. And again, because it's in JSON, I can decode it. I can pull the particular items out of that JSON message that I care about. So if I care about the data element, the name element, or the sensor element, I can do what I wish with it. And Node-RED is, again, built on top of Node.js, which is all JavaScript. So if you're able to program in JavaScript, you can do some pretty powerful things here. So in this case, what we've done was we've taken the incoming JSON messages, we flow it through this JSON node, which will basically turn my incoming string into a JSON object that can be parsable. And I click it into my switch function. So these are all nodes that I've dragged in from this palette. So if I double-click here in the switch, you can see that if message.payload.d.sensor equals a certain name, whether it's potentiometer, light, or water, I'm going to forward out that JSON message to a certain output pin, whether it's output 1, 2, or 3. And that's what's happening here. So if it's coming from my potentiometer, I'm going to send it out to this node. If it's coming from my light sensor, forward it to this node. If it's coming from the water sensor, forward it to this node. And these are nodes that are basically forwarding my data to my visualization dashboard hosted here in Freeboard. So this is the bridge, if you will, to my visualization tool. So you can see here, this is the data source coming from the Node-RED application. And these are the widgets that are hooked up into those data sources. So another thing I'll go ahead and show real quick is that we've also enabled remote notification. So I'm basically pulling out the moisture data. So again, if sensor type is water, we're going to output that message to pin 3. Output 3 is hooked up to this function block. And inside of this function block, I have a simple if statement. If message.payload.d.data is greater than 100, let's assume that water is being detected by my moisture sensor. And let's go ahead and send a string that says, alert, Adrian, your house is flooding, to the next node. So that'll flow out and hit this red node, which is Twilio. It's a cloud service for triggering text messages. So just like that, with very little code, I'm able to not only enable visualization, I'm also able to trigger remote notification over SMS by just dragging in the Twilio block and configuring it appropriately. So let's go ahead and hit deploy, and let's make sure that this works. I've got my moisture sensor here, and I'm just going to dip it into a cup of water. And hopefully I get a text message notification here soon. There we go. So you can see my text message just came through here that says, alert, Adrian, your house is flooding. Good luck with that. So just like that, we were able to enable remote notifications to my cell phone, and that was triggered by the cloud application that we just built together. So hopefully, sorry I went really fast. I really wanted to hit on all three of these points, but basically within about 30 minutes, we created a RF sub-gigahertz sensor node. We created three of them, one that detected moisture, one that detects potentiometer values, and one that detects ambient light. We also created our Wi-Fi gateway that's able to communicate to all of our RF nodes. And then we also created a cloud-hosted application for visualizing our sensor data and also enabling remote notification through text messages. As you scroll through here, you can see there's a lot of different nodes here. If I wanted to do things like data logging, I can do so as well. I simply drag in the MongoDB block, and this will data log all the incoming messages coming from my moisture sensor or my light sensor, and it'll actually save it into a MongoDB collection. So this makes it really easy to do real-world IoT applications that scale. Because we're using the IBM cloud in this instance, it's easy to go from one instance to 1,000 instances to 100,000 instances. And then obviously IBM will charge you appropriately, but it will scale as needed. So let me switch back to the slides here and close this out. So hopefully you guys were able to follow along there. Again, feel free to navigate to this URL here. You'll be able to follow along, rebuild the sensor node that I've created, rebuild the Wi-Fi gateway. I also provided the source code for the Node-RED flow that I've created. And let me quickly show you how to do that. When you're in the Hackster project page, if you scroll down to the very bottom, you'll see a Node-RED flow. Just go ahead and hit download, and you'll get what is basically JSON. This is JSON that describes the Node-RED flow that I'm using. So if you copy this and jump back to Node-RED, and if you have your own blank sheet here, if you actually hit Control-I, it'll bring in the import window. I think you can also access it from this window, so import from clipboard. And I can paste in that JSON code and hit OK. Oh, whoops, I'm not sure why that's not working actually. Let's see here. There you go. And now you get the exact same flow that I created. So that was all defined by the JSON that I just copied and pasted and imported. And now you have the exact same flow that I had. You might have to make some modifications. You probably want to change so you're not receiving other people's sensor data, so on and so forth. But for the most part, this should give you everything you need to create the sensor nodes, the gateway, and the cloud side of your application. And then one last thing, jumping back to the slides here. So again, there's two ways of getting access to this hardware that I've played with here today and demonstrated. First and foremost, you have the ability of signing up for a webinar or a chance to win the bundle. We have basically a simple quiz. So there's 5 questions that you can go ahead and answer, and the folks that answer the most questions correctly get a chance to win all of the hardware that I've demonstrated here today. So if you navigate to this URL, you'll be able to participate. In addition to that, as Dave mentioned earlier at the beginning, they'll be doing a road test where you'll be able to take the exact same hardware that I've played with, give it a try, and provide your honest feedback. It's something that we love doing, we love supporting. It's always great to hear the feedback coming from developers and engineers and makers, and this allows us to improve upon the hardware, software, and cloud side tools that we develop and our third parties develop to continually improve the development experience our customers go through. So please take a look at these links here, both the quiz and the opportunity to do the E14 road test. And then lastly, these are just some of the URLs that I've gone through here today. Feel free to navigate to any of them. There's various resources, various tools, various information presented at each of these links here. And we'll be sure to work with Element 14 as well as the TI.com web team to upload this presentation so that you guys can download it on demand as needed. So thank you so much for hanging out with me for the last hour. Again, sorry for going really fast. I wanted to cover all of this from an end-to-end perspective, so hopefully you were able to see some of that here today. And again, I appreciate you guys spending the time with me here today. And then lastly, last shameless plug, if you don't mind following me on Twitter. I do my best to keep that fresh and up to date, but you can follow me at Adrian at Twitter. So thank you very much. Dave, I don't know if you need to go ahead and do a quick outro, but for the most part, it was a pleasure presenting to everyone here today.
Great, and thank you so much, Adrian. It's a great presentation, and thank you for everyone who did attend the webinar. Adrian did a great job letting everyone know about the road test and everything else going on, so thank you. I will mention that there were a couple of questions in the chat and Q&A windows that unfortunately we just kind of ran out of time to answer, but rest assured we'll get those questions answered for you and posted on the event page at Element 14-webinars. Actually, the event page that you registered for the event for, we'll be posting those out shortly. So thanks again for the questions, and make sure you continue the conversation about these parts on the Element 14 community, and we will see you for our next installment of our Texas Instrument webinar series coming up next month. So thank you so much. Have a great day, everyone.
Hey, thanks, everybody.